All right, we're going to pick up with part H. Does it matter which experimental data we use in order to calculate the value of K? The answer to that question is no. We could use any of the experimental runs. I used number 3 and number 6. I got out my calculator, I ran all of the data, and in fact I get the same exact number, 2.7 times 10 to the minus 4th. Now, once I have that data, I can plug that back in, and now I can compute the rate at any concentration. So the problem asks us to compute the rate when both ammonium ion and nitrite ion are 0.100 molar. So I plug this in, 2.7 times 10 to the minus 4th times 0.1 times 0.1, and I get 2.7 times 10 to the minus 6 molarity per second. That's my rate because now I have the rate constant. These exponents, m and n, these are our reaction orders. Now, if the exponent is 1, we say it's first order. If it's 2, we say it's second order, etc. The overall reaction order is the sum of the orders with respect to each reactant. And most of the time in AP chemistry, they're going to be 0, 1, or 2. Now we need to evaluate a couple of statements. Statement J says the exponent for each substance in a rate law should be the same as the coefficient for that substance in the overall balanced chemical equation. Well, the answer to that is false. It might be the same and they might not. They will be for an equilibrium expression to tell us the extent of the reaction. But we're not talking about that. We're talking about the rate. And the only way to do this is to actually evaluate experimental data. So question K, the exponents in the rate law should always be determined from experimental data. And the answer to that is yes, that's true. The best way to determine if a reaction is fast or slow is to look at the magnitude of the rate constant. The bigger the rate constant, the bigger the rate. The units of the rate constant are going to depend on the overall reaction order. Now we have a table for some various rate laws, and we can look at the value or the kind of the significance of the concentration of my reactants to get an overall reaction order and the units of the rate constant for that reaction order. So in the first case, the rate is just equal to K. We do not include any concentration of any reactant, so that's going to be 0 order, and my rate constant is going to be molarity per second. The second one is when I have got the rate as a function of, or is equal to K, times the concentration of A. Well, that makes my reaction first order, and when I do that, my rate constant is going to be 1 over seconds, or seconds to the minus 1. And it really doesn't have to be seconds. It needs to be an order of time. Could be seconds, could be minutes, might even be hours. The third and the fourth line both are second order because in our case, it might be proportional to the quantity of A squared. It might be proportional to the concentration of A times the concentration of B. In either case, that's a second order, and I have molarity second, both to the -1 power. And our last case is when I have K times the concentration of A squared times the concentration of B, or it might even be B squared times A. But either way, that's a third order reaction, and my rate constant is going to have units of molarity to the -2 times seconds to the -1. All right, so we've got a few questions here. Suppose the rate law for reaction is rate is equal to K. If I double the concentration of my reactant A, what effect is this going to have on the rate? It's not going to have any effect because the concentration of A is not part of the rate equation. So I can do whatever I want to the concentration of A, doesn't have any effect. So suppose that that the rate is equal to K times the concentration of A. If I double that, I'm going to double the rate for obvious reasons. And then if it's a second order reaction and I double the concentration of A, I'm going to quadruple the rate because I'm doubling the concentration squared. All right, now we've got a problem here where we've got to actually evaluate some data. I'm taking mercury 2 chloride. I'm reacting it with oxalate ion forming chloride and carbon dioxide and mercury 1 chloride. And so I've got 4 experimental runs here with various concentrations, and we need to find out what is the order of this reaction. How do we evaluate what effect HgCl2 concentration and oxalate concentration have on the rate of this reaction? So part I says, what's the order of the reaction with respect to HgCl2? Now here we can evaluate run 2 to run 3, because when I do this, I see that, well, in runs 2 and 3, the oxalate is holding steady at 0.404. So I'm going to write kind of a big proportionality equation. And I look at the rate for number 2 divided by the rate for number 3, and I write out my entire rate constant general equation. That's going to be K times 0.0836 to the M times 0.404 to the N, and that's equal to 2.08 times 10 to the minus 4th. And then I do the same thing for run number 3, and I set it up as a constant, as a ratio of these two conditions. And when I do that, I see, well, the K's are the same in either case, so they cancel. And my 0.404 to the N's cancel, leaving me with just a way to evaluate M. So that becomes 0.836 divided by, or 0.0836 divided by 0.0418 to the M is equal to 2. So M in our case is equal to 1. We've solved that puzzle. Now let's go on to the next step. The next step is to evaluate this with respect to the oxalate ion. And we're going to do the same exact thing, but instead of comparing 2 and 3, we're going to compare runs 1 and 2. Because in runs 1 and 2, that's where HgCl2 is constant, but oxalate changes. So I set up the same exact kind of long setup here. And when I do, again, the K's cancel. And now when I do this, oops, rather than those two canceling, I've got my little lineouts in the wrong spot here. I can see that my 0.0836 factor cancels out, and I'm left with 2 raised to the n power is equal to 2. I'm sorry, is equal to 4, which is that's the quotient you get when you divide 2.08 divided by 0.520. So 2 to the n is equal to 4, n is equal to 2. So if I write the rate law for this reaction, I'm going to get rate is equal to HgCl2 raised to the first power times oxalate raised to the second power. The overall order of this reaction is 3 because I'm just summing the exponents. 1 plus 2 is 3. Now, how can I evaluate the rate constant? Well, I can use any of the, now that I know M and N, I can use any of these 4 runs. So I picked one, plug in the numbers that I know, and evaluate K. When I do, I get 0.0152 molarity to the minus 2, minutes to the minus 1. All right, now what is the value for the initial rate of disappearance of oxalate for experiment 1? Well, my rate of disappearance is going to be half the rate of appearance of my chloride ion. So therefore, that's 2.6 times 10 to the minus 5th molarity per minute. And if I want to calculate the initial rate of formation of chloride for experiment number 4, I can say the rate is equal to K times the concentration of HgCl2 times the concentration of oxalate squared. And now I can plug in all of these various numbers that I have, and I get 1.27 times 10 to the minus fourth molarity per minute. And you should make sure you can plug these numbers in and come up with these rates on your own. All right, let's look at the concentration change with time and see if we can get something that we can make sense out of. For a first order reaction, the rate law is rate is equal to K times A. And if I put this into calculus, which we are not going to do, I get that the rate law is the natural logarithm of A at some time t minus the natural logarithm of A initial is equal to KT. Let's define all of these terms. A initial, that's what it sounds like. It's the initial concentration of A at time t equals 0. A sub t is the concentration of A at some later time t. K is the rate constant. T is the amount of time since the start of the experiment. Now, let's rewrite this in the form y equals mx plus b, which would be a line. If I do that, I would get the ln of A of t is equal to minus kt plus the ln of A initial. All right, now, I've got a big table of data here. So here's my concentration of A, and you need to get your calculator, and for each one of these values of A, take the natural logarithm and fill in the data table. I'm going to let you pause the video, do those calculations, which will take you maybe 1 minute at the most, and then restart the video. When you took the natural logarithm, you should have gotten the following numbers. All right, now I want to plot. I'm going to do two plots here. I'm going to plot the concentration of A with respect to time and the concentration of the natural logarithm of A with respect to time. And if I do that, I see that a plot of A versus time gives me a curved line, but the plot of the natural logarithm of A gives me a straight line. And that's pretty interesting. So for a first order reaction, which of the following generates a straight line? And of course the answer is time versus the natural logarithm of A. All right, we want to calculate the slope of the straight line that was generated from this data and include units. And I can use any 2 points on the data because it's a straight line. So 2.07 minus 2.3 divided by 10 seconds, I get negative 0.023 reciprocal seconds. It's negative because it's disappearing. What does the value of the slope represent? It represents the rate constant K. Now for a second order reaction, I can write rate is equal to Ka squared. And from calculus, I'm going to solve that or integrate that, and I'm going to get that equation. And if I rewrite that equation in a linear form, y equals mx plus b, I'm going to get 1 over A sub t is equal to kt plus 1 over A initial. And I've got some additional data here, and I think you know what's coming. You're going to need to stop the video. You're going to need to take the logarithm of each of these individual concentrations and then take 1 over the individual concentrations. When you do, you get the following data. And when you plot these, each of these, A versus T, the natural logarithm of A versus T, and 1 over A versus T, you get 2 curved lines and 1 straight line. And we are going to pause the video right here and come back and finish in a minute.